Good morning, Nandalal. So we have to start at.
Good morning, sir. Good morning.
So it is 1 minute. Good morning. So we have to start now, so that we can start our lecture at 9 o'clock exactly, right?
Okay, sir. Okay.
Very good morning to the participants.
Peter joined.
Not yet, sir.
True. Okay. Okay. It is not for him only. So we need to
Before
introduce
that,
him.
there are few announcements.
Okay. Go ahead.
Yes,
Please.
sir. The participants who have not joined by their name are requested to rename themselves. Please log in by your name followed by your institution name. Secondly, if you have any queries at the end of session related to this topic, they can post their questions in the chat box. We shall open the chat box towards the end of the lecture, and please register yourself from posting not relevant messages like good morning messages. And third, we shall post one assignment at 4 p.m. Indian Standard Time based on today's session. So all the participants are requested to submit the assignment on time and as per the guidelines provided in the WhatsApp group. Thank you.
Hello. Good morning, everybody. People from India who has joined. It is 9 o'clock, and the people who are from African countries, they are at very early morning before sunrise.
Yes, sir.
Those from US and other parts. So now we are in third day of our training. This is a very nice presentation will be there from Dr. R. Troy Peters, who is a professor of biological systems engineering from Washington State University. So before he joins, or I hope he's joined, he will be joining soon. So I will be introducing him.
He has joined.
Yeah, he has joined. Nandalal. Yeah, Dr. Peters, welcome on board. Good evening to you, and greetings from MPKV Rahuri and India. So, good evening to you. Dr. Peters is working in the land, air, water resources, and environmental engineering. There is Lorry emphasis area is his primary focus on agricultural irrigation, which includes deficit irrigation, irrigation water hydraulics, irrigation scheduling, and irrigation management, also the irrigation automation. So all about irrigation, we'll be listening everything from him. Low elevation spray applications, he will be introducing to that also. So today's lecture is very important part as on the part of farmers and agriculturists who are working for saving their money and where there is least amount of irrigation water available, that will be helpful for managing the water. So cost effectiveness of irrigation systems and its comparative analysis we will be discussing about. So welcome to Peters. So I will hand over this session for his presentation. Nandalal, please go ahead for next thing. Thank you.
Thank you very much, sir. The organizing secretary for introducing Professor Troy Peters. Now I would like to request Professor Troy Peters, Biological System Engineering, WSU USA, to start your lecture and presentation.
Okay, great. So I am here. I work with Lavcot, and I do irrigation management and that type of thing. Let me just make sure that you are seeing my I hope that you see my screen.
Yes, sir.
Can you?
Yes,
Yeah.
sir. Yes, sir. Yes,
It
we
is
just.
visible to us. Please go ahead.
Okay. Okay, great. So what I wanted to talk about, so there's a lot of different new irrigation technologies, and many of them save water and they're being used in different areas. But I wanted to do a comparison of which of these what does save water really mean, and then compare the costs of these technologies, and then also compare how much water they save for the costs that these technologies actually cost. With that, what I want, a couple definition is, first of all, in order for us to, for irrigation, the amount of water that we need for irrigation is the consumptive use, or the amount of water that's actually used by the crop or evaporated, divided by the irrigation application efficiency. And that irrigation application efficiency is defined by the water that actually gets stored in the root zone, divided by the amount of water that flows onto the field. Okay, so what does that irrigation application efficiency mean? So for surface irrigation, we have water that flows here through across the surface of the field. The plants use water through transpiration, and then they also lose water through evaporation from the wet soil surface. Of course, we have runoff, but the largest loss of water in surface irrigation is to deep percolation, because we've got to have the water sitting, the water is at the top of the field for many hours, often before the bottom of the field gets any. So that means that we force water in order to adequately irrigate the bottom of the field. Then we over irrigate the top of the field, and so we have water losses to deep percolation. With drip irrigation, so not only do we have less water losses because we have less of the soil surface that's actually wet. So we have lower evaporation water losses, and the only source of water loss for drip irrigation is the evaporation from the small amount of water soil that's wet, and the amount of water that gets lost to deep percolation. So here, uniformity is really important. You can see in order to adequately irrigate all areas of the field, because of poor uniformity, then we have to over irrigate some areas of the field. So uniformity is required for efficient irrigation. With sprinkle irrigation, we have water losses from the wet soil surface. We have water losses from the wet leaves, and we have these spray losses. So as the water travels through the air, we have wind drift and evaporation from these droplets, and those are losses. And then again, the uniform application of that water is important for overall irrigation efficiency. But let's talk about on a big scale. Let's say we have a closed basin. So this is a state or an area and then we have precipitation in. We have surface water that might run in through here through a river, and then we have surface water that runs out. Okay, the only other thing the biggest source of water loss is through evaporation out of that area, or the change in storage. So if we can store water into the ground and store water as groundwater, or we can pull that water up out of that ground. But of those, the true water losses are these what I call forever losses. So water losses to evaporation and consumptive use, those losses never come back. However, some water losses in terms of irrigation, like runoff and deep percolation, it's possible that we can retrieve those and use that water again. So it's not always losses, and it depends on your aquifer, how easy it is to get that water back out of the aquifer that we lose to deep percolation, runoff off the bottom of the field, how easy it is to reuse that water. So in many cases, those losses aren't really losses. In some cases they are, but in some cases they're not. However, these evaporation losses are almost always true losses. Of course, we can't, and that's the largest source of water losses. So like this leak on this irrigation system, of course, what it's doing is it's causing water to pond in this area, and that water will go into the soil, and it will cause non-uniform irrigation. We'll have too much water here, and that water will go into the soil, be lost as deep percolation. So, but those losses might be recoverable eventually. They're always lost to the grower. He loses control of it, and he loses control over the timing of when that water is available. But that water might be recoverable eventually. And then these are forever losses. So here's a center pivot irrigation system, and you can see that, you know, this is a windy day, that water is blowing away on the wind. Those losses will never return, at least that we can track. Again, this big gun sprinkler system, you can see the wind blowing that water away. Huge losses, actually. If we measure the amount of water that comes out of that nozzle, and then we capture the amount of water that's on that actually makes it to the soil surface, we're only catching about 60% of the water in this case. So 40% of the water is lost from the time it leaves the nozzle until it reaches the soil. These are significant, and they're permanent. Irrigation efficiency depends on the operation, how that irrigation system is operated, the timing, the amounts, the frequency, that the irrigation system, like the nozzle sizes, the pressure differences, things like this, the maintenance of that irrigation system, the weather, when it's really hot and windy out, the irrigation efficiency goes down. And when it's cool and humid, or it's raining or something, then the irrigation efficiency is very high. The flow rates onto the field, and then the field and soil properties, depending on the irrigation system, like the slope of the field, the infiltration rates, the water holding capacities. So thus, irrigation efficiency varies field to field and throughout the day and through the season, but we need to have some number that we can use for irrigation efficiency in order for planning. And so here's a table of numbers that we put together, the average irrigation efficiencies for these different types of systems. Drip irrigation systems, the irrigation efficiencies are very high. Sprinkler irrigation systems, it depends on the type of sprinkler irrigation system. Basically, the longer the water spends in the air, the less water makes it to the soil and the more is lost. So the higher the sprinkler is, the higher the pressure is, then that affects the irrigation efficiency. And then surface irrigation. Surface irrigation has the highest variability. You can have extremely, almost 100% efficient surface systems under the exact right conditions, the exact right flow rates, the exact timing, you take it and then you shut it off. And usually for those, it requires really high flow rates, and high flow rates, of course, cause erosion. So surface irrigation can be efficient, but it most often is inefficient. But with surface irrigation, the losses are almost recoverable eventually. With sprinkle irrigation, those losses are almost always the largest source of those losses is not recoverable. So it's different. So something to think about. So efficiency measurements, this is how we can measure. We measure the amount of water that comes out of the sprinkler nozzles, and then we can calculate based on the spacing and how fast that machine is moving, etc., how much water should be getting into those catch cans. And then we divide. And then in this case, center pivots, for example, we've tested them many different times, and we get 80 to 85% of the water that leaves the nozzles we can catch in these cups, these catch cans. So 15 to 20% of the water is lost before it reaches the ground. You can also test it using these lysimeters, where we capture the water that percolates through the soil, and then we can close that water balance. This is a way that we can use to capture deep percolation. So we did a bunch of these different types of studies. And then you can see, so we did it with, there's a standard catch can test. We did it with electrical conductivity. So basically you measure the EC of the water, the irrigation water before, and then you measure the EC of the irrigation water as it's in, when it's in the catch can. And that will give you an idea of how much water was evaporated from the droplets as they flew through the air, because clean water is evaporated and leaves the salts behind in the droplets. And so we did it this way as well. And then we also did some physical mathematical energy balance modeling with it, and you can see that there's these differences. So these are wind drift and evaporation losses during the daytime with these three different methods. This is catch can, this is the EC method, here's this physical modeling, and you can see the differences in those efficiency measures. Which is right? It's hard to actually know for sure. So this is another thing that we found. We measured the irrigation application efficiency of a MESA system and a LESA system, which I'll explain in a minute. And we found that those differences depends on the weather. You can see the May, June, July, August, September. So in July, it's very hot and very humid and very arid. And then we had much greater difference between the MESA and the LESA system when it's really hot. So basically that again shows that this depends on the weather. I also want to talk about one. So usually with irrigation systems, it's not really the total quantity of water that is used. That's not the problem. Usually the problem is the timing. So this is the irrigation water required throughout the season. So we have time, and then so being able to meet the irrigation water needs during the hottest part of the summer is the biggest problem. That's when we have the greatest need. That's usually when the crops are the most sensitive to water stress. And that's also when we have the least amount of electricity capacity or energy capacity to do the pumping, because everybody has their air conditioners on, etc. And so this creates capacity problems for the irrigation systems, as well as the energy supply companies. So being able to save water during this hottest part of the season is the most important. And we can see that some of these technologies save more water during this time of greatest need, and some save water during times of when we don't need it. So for example, irrigation scheduling. Irrigation scheduling is timing when to turn the water on, when to turn it off. Usually saving water, we've shown that irrigation scheduling saves a lot of water, but when does it save it? It saves it early in the season and it saves it late in the season, because they're irrigating like this when they don't need to be, and then they're irrigating up here when they don't need to be. But usually during the middle of the summer, the irrigation system can barely keep up anyway. So that, of course, they're not saving any water. So with irrigation scheduling, they're saving water at times when they don't really, fewer people care about that. So that's important to pay attention to as well. So what we did is we looked at all these, we kind of took all of these, the overall water losses from these different irrigation technologies. So here's the subsurface drip irrigation, mobile drip irrigation, all these different technologies. And then we fractionated which of those losses were forever losses. The blue is the forever losses. In other words, evaporation losses, it's gone forever. And then the remaining losses are the rest of the losses. So they're losses to the farmer, they're losses to the irrigation district, but they're still in the basin, they're still recoverable. So of course, you see these flood irrigation and some of these other methods have higher losses, but some of those losses are more recoverable. So if we sort by the forever losses, you see some of these surface irrigation methods that even though they have a lot of losses, they're not very efficient. Most of those losses are recoverable compared to some of these irrigation systems like a big gun or a pivot, a center pivot where you got the sprinklers that are on top of the pipe. Those have very high losses and the losses are forever, they're permanent. So in that case, converting from some of these like basin graded border, some of these surface irrigation methods, and converting to like solid set or hand move sprinklers, that may not be what's best for your region. And again, those losses depend on the weather, operating pressure, and a lot of different things. So, but that's something to think about. We put together a table of, how much water you can save by converting to the different technologies. So we also wanted to do the cost, right? How much does this cost? So we wanted to get cost per acre per year to implement these different technologies, these water saving technologies. So we wanted to include the equipment costs. We wanted to include the upfront labor costs, because it costs money to set these things up. You've got to hire people. You've got to spend management time that could be spent doing other things, but the manager's got to be out there and it's got to be ordering the right parts and organizing the labor and making sure everything's done right. After that's set up, they have weekly recurring costs, and then they have annual recurring costs with some of these technologies. So we wanted to include all of these and come up with the total cost per acre per year for these different technologies. And then we wanted to look at a percent water savings possible for these technologies as a percent. And then we just use a common water requirement of about 1 meter of water per year. And then to get a cost per acre inch of water that is conserved. Again, we're trying to get to a bang to the buck. And then, of course, the same with irrigation efficiency, there has to be these caveats, right? Okay, we put cost numbers together, but as soon as you put a cost number down, it's wrong, right? Because it changes all the time. Labor rates change all the time. Equipment costs change all the time. The materials costs change all the time. And so all of these things isn't well defined, but doing it one time still, I think, makes it a useful exercise. And people have to do these in order to make decisions based on what it is today. So the technologies that we studied were system conversions, converting from one irrigation system to another. We wanted to do the cost per acre inch conserved for data-based irrigation scheduling, including soil moisture sensors, where the grower buys and owns and installs and uses these sensors that he has, or where they hire a service where they talk to a professional who comes in and brings in the soil moisture sensors, and they hire them every year. They pay them so much every year to bring this in and to set this up for them. And then there's ET-based irrigation scheduling, which is at least here, it's using weather data to estimate crop water use, and we assume that that's free. And then we wanted to look at complete irrigation automation. The system turns itself on and off. This is a technology we have been able to do this for a long time. It's not difficult. We can do this, but it costs money. So we wanted to include this. Variable rate irrigation, which is varying the amount of water that's applied to the different areas of the field. So variable zone irrigation system and variable speed irrigation systems. We also wanted to look at low elevation spray application, which is a modification of center pivots, and then low energy precision application. I'll explain that a little bit later. Mobile drip irrigation for center pivots. I'll explain that. And then deficit irrigation, which is basically I irrigate one crop less, and then I irrigate either more land, which is what we call water spreading, or where I don't irrigate more land. And then tillage practices, where we use it to control the runoff. When we use dammer dikers, we can increase the soil surface storage, and then we can get more water into the soil with this. And then also conservation tillage, no-till and strip-till, where those also save water. So we put together cost estimates for each of these, cost per acre per year. So here's soil moisture sensors, where again, where somebody buys and installs these. Here's irrigation ET-based methods, where we get weather data, and then we do irrigation scheduling just based on ET. We assume that this is free, and the only cost is management time and attention. There's also simple ET-based methods. This is what we call a Woodruff chart. Uses historical average crop water use for a particular crop in a particular area, and that's a simple way to do that. Irrigation automation, which is precision irrigation. So again, turning itself on and off. And then variable, this is variable rate irrigation, variable speed irrigation, and then variable zone irrigation. Variable speed, at least with a center pivot, is where you just vary the speed of the pivot as it goes around in a circle. Where it goes fast, it applies less water. Where it goes slow, it applies more water. But with variable zone irrigation systems, we have banks of sprinklers that are turning themselves on and off along that, along the sprinkler, in order to apply different amounts of water to different areas of the field. Of course, this method limits itself to these pie-shaped wedges, but this has much more flexibility in what you can apply to different areas of the field. So this is becoming more and more interesting and useful because we are irrigating more and more marginal ground that we're trying to produce crops on. Basically, with variable rate irrigation systems, it's important to kind of think of this. So we have different types of soil in the same field. If I have a deep silt loam soil, I have a very large water holding capacity. If I have a deep sand or a shallow sand or a shallow silt or a shallow sand, ET, the amount of water that the crop needs is pretty much the same in the entire field if I get maximum yields. And that means that if the only time that it makes sense to apply variable amounts of water to these variable areas is if I've depleted all of this and then I want to make space in the soil for rainfall. So if in this area, we get very little, almost zero rainfall during the irrigation season, during the growing season. And so variable rate irrigation doesn't make very much sense because ET is the same. However, if I do get a lot of rainfall during the season, I can save water by irrigating this sand and then allowing this to deplete in order to make space for the rain to be held in these soils with greater water holding capacities. And so that is, and if you have fields that look like this, where you're trying to avoid irrigating non-crop surfaces, it makes sense to use variable rate irrigation. Otherwise, if it's a very dry area, it doesn't make very much sense to use that. No-till and strip-till, basically by leaving the residue on the soil surface, not only do I use less tractor time, but it saves water and it builds the soil structure. It's actually very good for the soil to do this. It increases the infiltration rate of the water. The water goes into the soil a little better, and then the water stays in the soil a little better because the soil is shaded and protected from evaporation from the sun. These technologies save water and they save work. If you can, the only problem is trying to get the seeds germinated. However, most of those problems have been solved by farming equipment manufacturers. The other technology that we looked at was these different types of sprinklers on center pivots. Center pivots irrigate about 80% of the ground around here. And so if we have high pressure impact sprinklers on top of the pipe, that water spends a lot of time flying through the air. It exposes itself to a lot of opportunity for evaporation and for the wind to blow it away. Not only that, we have what's called wind shear, where the higher you go up, the faster the wind speed. And so we have this exposes this water as it flies through the air to greater amounts of air for evaporation. And that's really, so we have spray losses of 30 to 40% when it's up in the canopy like this. Most people around here have converted their irrigation systems to what's called mid-elevation spray application, LESA, where we have a sprinkler that operates at the bottom of a drop here. And then these losses are about 10 to 20%, but this is what's called low elevation spray, where we can move these drops all the way down right next to the soil surface. And the wind speed down here is almost zero, and it gives very little opportunity for evaporation because we're not wetting the canopy, and we are protecting that water from evaporation. So here you can see MESA sprinklers in the background and LESA sprinklers operating in the foreground. Here is LEPA, it's called low energy precision application, where the water dribbles directly onto the soil surface. In this case, you have to do tillage that prevents the water from running around the field. Otherwise, the water will just run off. But in this case, they use what's called a furrow diker, where it pulls and it pops up these little dikes in the furrow right here that holds the water in there. Not only that, they're irrigating every other furrow so that this furrow stays dry to limit the evaporation from that furrow. With this method, they can apply up to 25 millimeters of water per irrigation, and they're very efficient with it. One of the problems with this technology is you're applying the same amount of water in less time in the same area. So in this case, you have a larger spread. So as that pivot moves by, it gives that soil more time to take that water in. Here, there's less time, and so it has a greater propensity for ponding and runoff in this case. So if you have a soil that's already having problems with runoff with your sprinkler system, this technology is not going to help you. It's going to make your problems much worse. The other technology that we have is called mobile drip irrigation, is where we have center pivots that drag drip tubing, basically. So this is drip tubing, and there's holes in this drip tubing that goes all the way along, and we can drag that drip tubing. What's really good about this is that it applies the water very slowly over a very large area, so that really reduces the problems with runoff. It also has all the benefits of reducing evaporation from a wet canopy and from a wet soil surface. You can see here where this was with mobile drip irrigation, and then this was with sprinklers right next to it, where the mobile drip irrigation got the same amount of water into the soil, but it left a lot of the soil surface dry to limit evaporation. So then the other thing is that we also looked at was called deficit irrigation, where generally the more water you apply, this is to a crop, the better you get the yield. However, at some point you reach a maximum, and then you come back down, and you actually you reduce yields by applying more water. So there is a point here, however, that we can reduce. Usually it's about 20 to 25% of the water, and then we have only a very small reduction in overall yield. So that's this has been shown with a lot of different studies that say you can cut back, 20 to 25% of the water, and you might lose 5% of your yield. So if you could take that 25% of your water and move it to another area, and then irrigate additional ground, there's potential for the farmer to make more money by doing it this way. So here's some more with no-till methods. And then also this is tillage to increase soil water, surface water storage. They run these dammer dikers that pokes holes basically in the soil, and it makes it so that the water cannot run off of the field, and it holds it there, and it increases the soil surface water storage. So this is, we put together the total estimate of the total water conserved. So here's the total the cost per acre inch conserved per year. So here's all of those technologies sorted based on their costs. So a positive number is a cost. A negative number means that they can actually make money. So this is deficit irrigation with water spreading, conservation tillage. Growers can actually make money because they can reduce and basically because they spend less energy, less money on tractor, diesel, and time and labor time to till their fields with this. Even with the additional cost of this newer implements like the no-till drills and things, they can make money with this tillage. So deficit irrigation, they can also make money with. This is a little bit of a misnomer, because if they spread the water, they're not going to save any water. They are going to use all of the water that they're allocated. And so here are the other technologies. So all of these other technologies actually, we estimated, will cost the farmer a little bit of money to implement. So because we didn't assume that there was yield increases. So LESA, this is the low energy precision application. This is the low sprinklers on center pivots. Here's ET-based irrigation scheduling, mobile drip irrigation, soil moisture monitoring, where they own the sensors, soil moisture monitoring, where they rent them out, have somebody else come and do it. tillage to reduce runoff, dam or dike, irrigation automation. You know, it saves water, but it's expensive. Deficit irrigation without water spreading, which is why farmers, if you say they can't keep the water that they save with deficit irrigation, they're not going to do it. And variable speed irrigation, and then variable zone irrigation. These are the variable rate irrigation technologies. Save a very small amount of water, at least in our area, and they're very expensive. At least they are right now. So that's what we put together. So what are our recommendations based on this? I think so if we want to save money and save water, then it's good to support irrigation management, education, outreach, and demonstration projects. Especially there's surface irrigation, irrigation scheduling, and interpreting soil moisture sensors. There's a lot of these technologies that save water, and the growers would do them if they knew how to, and understood the real benefits of that. So in some cases it costs them money, and then so then it doesn't make sense for them to do that. So and then also prioritize the biggest bang for the buck technologies. So do the, you know, in a region, they should do some of these other technologies like the low sprinklers, the irrigation scheduling, which is free, soil moisture sensors. These things are the lower cost technologies. And then move towards on-demand water delivery. So if in an irrigation system, if you want growers to be able to do a really good job of water management and reduce their water use because they're applying the right amount of water at the right time, then they have to, it helps them if they have on-demand water. So they need to be able to turn the water on when they need it, and they need to be able to turn it off when they need it. This is very difficult for irrigation districts and governments to do, to supply on-demand water. It's much easier to supply them a constant flow rate, but sometimes to do good irrigation management, they need large flow rates for short amounts of time. Again, this is expensive for governments and irrigation districts to do. Avoid big guns on pivots and on the carts. Those high pressure sprinklers are expensive. And then think twice about converting to hand lines and wheel lines too. These type of high pressure impact sprinklers, they might not benefit the area as a whole. And then drip irrigation, of course, move towards those if they can afford to pay for that drip irrigation by the improved quality and yields, can often justify that cost, additional costs. So again, these are the technologies that we think should be prioritized. This conservation tillage, LESA, ET-based irrigation scheduling, mobile drip irrigation, some of these other technologies that can save a large amount of water and then for lower cost. And then again, keep this in mind, the fraction of forever and short-term losses to the whole area of these different technologies. Think about that in terms of where the water goes and whether that water is actually recoverable or not. And prioritize. So again, some of these surface irrigation methods may not, they're not as bad as many people say, as long as you have methods of eventually recovering that water. The other thing is, a lot of times we pressure growers to adopt some of these irrigation technologies, and then so I think it's like, I think some of that's the same as asking them to just be kind and pay extra taxes. So don't you care about the environment? Don't you care about the country as a whole? Sure they care, but they're just not willing to bear those costs all by themselves. So if we want growers and farmers to implement some of these water saving technologies, we have to either create laws that punish them to basically force them to implement these technologies, or the public can share in the costs with the individuals. You can say, oh, if you implement this technology, the government or the taxpayers as a whole, we will, pay 30% of it or 50% or however you want to do that. That makes it so that it's cost effective for the grower, and then that's better for everybody. And that's about it. I think we're about done. Okay, I think the rest of this. So the biggest opportunities for Western United States with this is this no-till, strip-till. We're trying to get the water laws changed to allow them to spread their water to additional acreage. That's a very difficult thing to fight politically. And then this LESA mobile drip irrigation in this order, I think makes a lot of sense, at least for this area. And then drip irrigation on high value crops. With that, I'm done. Does you have any questions? Let me see if I think you can post them in the chat.
Yes, sir. There are a couple of questions from the chat box. With your permission, shall I take one by one?
Yes, sure.
Yes, thank you, sir. Dr. Arun Banerjee, he's asking about the best type of soil moisture sensor in terms of accuracy and low cost option for ground truthing with the satellite-based soil moisture data correlation.
Right, that's a good question. I have worked with a lot of different people who've evaluated a lot of different soil moisture sensors. And so the bottom line is that all of them have problems. So, and a lot of, I've become very frustrated with using them in general. However, it doesn't, so if I expect the number to be exactly right, I'm going to be very frustrated. But if I look at that number and use the relative, just take that number as a relative number, and then watch the dynamics of how that soil moisture sensor changes over time, then those soil moisture sensors can become really useful. So basically, with soil moisture sensors, we need to know where field capacity is, where is the soil full, and where is the crop going to begin to experience water stress. So if we know those 2 points, then we can try to keep the soil moisture content between those two. And we can often derive what those 2 points are just by looking at the sensors. Whether or not that number is actually accurate is less important.
Okay, thank you, sir. Dr. Daya wished to know that for farmers of India growing in sandy soil, so what amount of pressure you would like to suggest for a drip and sprinkler system? Also, he want to know that what type of nozzle are most suitable to control water wastages.
Yeah, so okay, so with so pressure depends on a lot on the kind of irrigation system. So, and unfortunately I'm not very good with my SI units, but it's about I think it's about 1 bar or less is what will be used for drip irrigation, and then like 2 or 3 bars for sprinkler irrigation. And then so sprinkler irrigation requires the pressure in order to throw the water and also to disperse the stream. Because it's like I showed, it's really important for the irrigation system to apply water uniformly. And if at low pressures, sprinklers, the stream stays together and it just hits in one location. And so we need a little bit more pressure in order to spread that out.
Oh.
And I forgot the other part of the question. I apologize.
Nozzle type. Which nozzle type is
nozzle
is more
type.
suitable to control water wastages?
Yeah. So what you want is you want a so you want uniform distribution and you want a large droplet, because a large droplet has a smaller amount of the water surface exposed to the air for evaporation as it travels through the air. But those two things don't always work together. So a sprinkler needs to break that stream up in order to apply the water uniformly. And but whenever you break that stream up, you're causing it's less efficient.
Okay, thank you, sir. Dr. Mohanty is asking how the conservation practice and variable zone irrigation affects the crop productivity as well as the BC ratio.
So it depends. So variable zone irrigation systems. So Dr. Kotz, who's my colleague here, he's doing we're working together to use drones and remote sensing to estimate crop water stress and crop water use. And so variable ET throughout the fields, if one area is using less water, then we can actually apply less water and save a little water there. But usually we assume that ET is about the same throughout the whole field. Yeah. I'm not sure if I remembered the rest of that question.
Okay, shall I take a few more questions?
Yes, please.
Okay, Mr. Deepak Kumar is asking which type of irrigation is more applicable in hilly areas where the high erosion rate is there?
Yeah, in hilly areas, drip irrigation works for everything, right? So because the water is supplied so slowly, it does not create runoff. Sprinkler irrigation can only work in hilly areas if the application rate is very slow. It has to apply the water very slowly. And so some sprinkler irrigation systems apply the water slowly and some don't. So you would just have to, like hand lines and wheel lines actually apply the water slowly in a large area. So that might work a little bit better. Center pivots working good in hilly areas if the soil has a high infiltration rate. And if you have runoff problems, the water running off the soil with center pivots, you just make them go fast.
Okay, probably all questions are over. Still, I take one more last question. Dr. Safal Rai is asking for how long we can use the drip irrigation system in our farm if you install once.
There are buried drip irrigation systems that have been in use and are continuously in this area or in Kansas actually for like 25 or 30 years. So if the drip irrigation system is maintained properly, then it can last a very long time. The biggest problem with drip irrigation is plugging. Very small bits of junk in the water will plug those emitters, and if you plug the emitter with something that you can't dissolve with chemicals, like if it gets plugged with dirt or sand or something, it's not possible to unplug it. You have to rip the irrigation system out and put a new one in. So you have to keep the water very clean and manage the water chemistry so that it doesn't plug those emitters.
Okay. Thank you very much, Dr. Peters, for very informative and interesting lecture. Now, I would like to request
Dr. Deshmukh, there are still more questions. One question is that, sir, can you please explain LEPA, LESA, and MDI? Because many of the participants may not know what is LEPA, LESA, and MDI. Maybe may I request you to explain the principle behind those systems actually.
Sure. I apologize. I didn't go over that very well. Go back. I will show. So LEPA stands for low energy precision application, and what that let's share the screen again. Okay, share. So this is low energy precision application is where the water dribbles basically directly onto the soil surface. Low energy because it uses low pressure precision application. So this is a very efficient technology. This is mounted on a center pivot. LESA is also mounted on a center pivot, low elevation spray application, where it comes down and the sprinkler is maybe 30 centimeters from the soil surface, but it still goes through a sprinkler and it spreads the water out and it applies the water through a sprinkler. Compared to this is called mid-elevation spray, where the sprinkler applies is maybe 1 meter or 1.5 meters from the soil surface. And then mobile drip irrigation is MDI is where you drag drip hose. Mobile drip irrigation, you're dragging drip tubing on the center pivot as it goes around in a circle. So all three of those, LEPA, LESA, and MDI are modifications to center pivot irrigation systems to save a lot of water.
Okay, thank you, sir. One more question. Deepa Kumar from Jammu has a question. Which type of irrigation more applicable in hilly areas where the high erosion rate?
Hilly areas with high erosion rates. So what we're looking at here is mobile drip irrigation, where it applies the water slowly. Then you want to avoid runoff, which means you need an irrigation system that applies the water slowly. This is one method that can do it. Regular drip irrigations, where you just have set drip tubing, will also is very good for hilly areas. I've seen a lot of farmers around here that are growing apples are using micro spray, these micro sprinklers in between each of the apple trees, and that also works well because it applies water very slowly.
Okay, Mr. Balaguru has one question. Please suggest the irrigation system used in tree crops along with intercropping.
With tree crops and intercropping. So with tree crops, what most people do is micro sprinklers actually, or under tree sprinklers, where they're solid set, which means the sprinklers are buried in the ground, the pipes are buried in the ground, and all the farmer must do is turn the water on. There's other ways to do this where you put pipes out in between the tree rows, and then you move the pipes, but that is not common in the US because labor is so expensive.
Okay, thank you very much, sir. For the information of all the participants, there are still few questions and queries. We shall try to pass on those to the experts and convey you the response of experts through WhatsApp group and emails. Now, I would like to request Dr. Mukund Sinde sir, organizing secretary of this training program, to propose vote of thanks and introducing our next speakers.
Hello.
Yes, sir.
Thanks, Nandala. Hi, Troy Peter. Actually, we wanted to make aware the participants. We have more than 800 participants, and from different countries, of course, majority from India. And we wanted to make them aware about the different irrigation practices which are being adopted in Western USA. And you did a wonderful job. Thanks on behalf of our university and the Center for Advanced Agricultural Science and Technology. It was a thorough discussion on different irrigation methods, efficiencies, and cost saving. Thank you, Troy. Thank you. Thanks.
Thank you for the opportunity. Thank you.
Okay. Thank you, sir. We are now start the second session of the day. The expert is Mr. Abhilash K. Chandel, PhD scholar, Biological System Engineering, WSU Pulam, USA. So on the behalf of CAST project of Mahatma Phule Krishi Vidyapit Rahuri, I extend warm welcome to you, sir.
Thank you very much.
And now I would like to request Dr. Mukund Sinde sir, organizing secretary of this training program, to introduce Mr. Abhilash Chandel to our participants.
Hello. Hi, Abhilash.
Hello, sir.
My privilege to introduce you. Dear participants, Mr. Abhilash is a PhD candidate and graduate research assistant at Biological Systems Engineering at Washington State University, Pullman. He received his BTech in Agricultural and Food Engineering and MTech in Farm Machinery and Power Engineering from Indian Institute of Technology, Kharagpur. And currently he is pursuing his PhD in Precision Ag, supervised by Dr. Love Khoth. Already we have listened to Dr. Khoth. So Abhilash is a student of Dr. Khoth. His current research is focused on drone-based high-resolution geospatial remote sensing of irrigated field crops and perennial specialty crops for water use, yield, crop stress, that is biotic and abiotic both, and vigor mapping. He is also involved towards smart spray application technologies and crop physiology monitoring using proximal sensing techniques. He is a member of the American Society of Agricultural and Biological Engineers and International Society for Horticultural Science, and also he's member of Indian Society of Agricultural Engineers. So, Abhilash, up to you now.
Thank you very much.
Yeah.
So can you see my screen, everyone?
Yes, sir. Yes.
Okay, great. Can you hear me loud and clear?
Yes, sir. Fine,
Yes,
fine.
Okay, great. So I hope you can see the full screen mode.
Yes, sir. Yes, sir.
Okay, great. Okay, thank you very much for inviting me in this seminar series. And it's my privilege to be part of this series. And thank you, everyone. So let me just quickly begin with my today's topic that I'll be delivering on the drone-based thermal and multispectral remote sensing with metric energy balance model for geospatial crop water use mapping. So my contents will consist of brief background, the project goal, unmanned aerial systems and optical sensors, brief introduction about them, the data pre-processing methods, what do we do of that data when we collect what we collect from drones, and then implementation of the metric energy balance model that estimates the actual crop water use, that's evapotranspiration. And then I'll focus some light on ongoing and our future efforts for some of the case studies. So water, as we all know, is the most critical resource. And some of the basic facts are that it covers 70% of Earth, of which 90% is stored in oceans and seas. And only 8% is available as the fresh water, of which ultimately irrigation consumes 70%. So that's how the water is distributed, and we know the importance of the water. So rising concerns in today's time is about growing population, rising food demand, climate change that is negatively having impacts on our production agriculture. The rising of arid and semi-arid regions, area under irrigation is increasing. And on the other side, we have the freshwater availability going down, the net cultivation area going down because the population density is increasing. Then the rainfed agriculture is also getting reduced day by day. And certainly at the last, since we are pumping or we are using a lot of groundwater for irrigation, its level is also depleting. So current irrigation practices are majorly constant or over irrigation. Basically, either you apply a one rate of irrigation to the entire field, so either it's at a constant level or you are just over applying your water. So what is the need? The need is having precision irrigation management and also having uncompromised production quality and quantity. So the brief background about water use cycle is the input goes from irrigation, precipitation, and the output is in terms of losses such as runoff, deep percolation, and the soil that loses water to the atmosphere is termed as evaporation, and the water that is lost from the plants is termed as transpiration. And the combination of both is called evapotranspiration. So when we talk about what is the water demand, it's actually the evapotranspiration which is used by the plants. So there are different methods of estimating evapotranspiration, starting from the smaller point scale. We have soil moisture sensors to measure them, lysimeters, we have soil moisture probes, different moisture probes. We can measure crop gas exchange through the leaf level stomatal conductance. We have leaf porometers that also measure stomatal conductance. And then we have sap flow sensors that actually measure the transpiration of typically the tree crops. But one of the major limitations is that these have limited sampling accuracy and may not be able to assess spatial water use variability because you need to install them or you need to use them at multiple locations within the field, and that makes it more laborious, expensive, and tedious. Another methods are gross scale methods, typically using standard crop coefficient and weather data, calculating the reference ET from the weather data and multiplying that with the standard crop coefficient. So basically, that gives you just one value of the crop evapotranspiration, and that is a general practice what growers across the globe are using. The another method is estimating the eddy covariance gas energy exchange. So there is an energy exchange between the atmosphere and the land surface, and that's what eddy covariance system measures. And again, it's just one value for the entire region, so you have limited possibility to assess the variation in crop water use. Moving next, we have regional remote sensing approaches, starting from the high orbital satellites. For example, Landsat 5, 7, 8, and MODIS. These provide us thermal and multispectral data. And since these are high orbiting satellites, the spatial resolution is quite low, approximately 30 meters per pixel for the Landsat satellite, 1 kilometer per pixel for the MODIS satellite. And temporal resolution is also low, nearly 16 days for the Landsat and 8 days for the MODIS. One of the major challenge here is these images are very much interfered by clouds and which cannot be controlled. And therefore, it leads to either no estimation or inaccurate estimation. Additionally, when we want to estimate the water use of perennial specialty crops. So perennial specialty crops are tree fruit crops, basically. So you want to estimate the tree level or the tree row level water use, you may not be able to estimate the water use with such a low resolution. So again, when we talk about these technologies, these are restricted for spatial and temporal variability assessments at field scale. Moving on is the regional scale remote sensing, again, using low orbital satellites. One of the major limitations with them is that they don't have thermal infrared wave bands. And to be noted that the temperature gradient between the air and the crop surface is one of the major driver of the evapotranspiration. And hence, if we estimate ET using the crop coefficient and vegetation index approach, the accuracy or the estimate would not be that accurate. Again, these are limited due to cloud cover interference and again restricted for perennial specialty crops. So this is one typical image where you can see this is an image of the land taken by the Landsat satellite, and we see the clouds. So if there are clouds, either you will have no estimation or inaccurate estimation. There have been methods that try to remove clouds using the image from the neighboring day or from the next day or subsequent day. But sometimes it does not represent the true picture of your crop physiology. Then what is the solution? We should move towards site-specific remote sensing. Why? It provides you more control over the data. You can have quality imagery on demand, and it has the quality of retrieving surface properties. And in that time, when you plan your drone data collection, you can certainly avoid the cloud interferences. So there's a high possibility that you can estimate the spatial variability within your field about the crop physiology, or in this lecture, when we talk about is about the crop water use. So this is a simple depiction of the energy balance concept, which is the metric energy balance model. This was developed by Allen in 2007. And this is the expansion is mapping evapotranspiration at high resolution with internalized calibration. This was typically developed for satellite-based imagery, that is Landsat 7, 8, and MODIS. And thermal infrared imagery is one of its critical input. Some of the advantages are it is independent of crop specific, so you don't need to supply much added information about your crop. And it is robust and widely adopted in almost over 25 countries. One of the most important features is that it calibrates the energy balance using extreme hot and cold pixel. Hot pixel corresponds to the bare soil, which does not transpire, which is not losing water. So that is one end, and the other end is the cold pixel, that is like highly transpiring vegetation. So the energy balance is calibrated between these 2 points, and that's where its accuracy improves or the biases are negated. One of the another thing is that it stabilizes the sensible heat flux computation within the blending height. That at the ground surface, the wind variability will be too high because of the rough surfaces. So you need to have stabilized sensible heat flux that could actually let you know the accurate amount of water that is lost from the crop surface. So the energy balance concept is the latent heat is actually equal to the net radiation falling onto the ground, the soil heat flux lost from the ground to the soil, and the sensible heat flux lost from the crop surface to just above air. So our project goal basically that we framed up is, why not use the US-based imagery, that is high resolution imagery with the metric energy balance model, so that we have high resolution crop evapotranspiration at field scale, and that could actually help us in monitoring or regulating site-specific irrigation management. So the brief schematic here indicates that using the drone-based images that are multispectral images from different visible and near-infrared wavebands, and the temperature image, when coupled together and used as inputs to the metric energy balance model, may produce accurate or reliable crop water demand maps, and then you can control that towards site-specific irrigation management. So I'll briefly touch upon some of the unmanned aerial systems that are used for agricultural purpose, except for spraying. So one is the fixed wing. The advantage is it provides long flights. It travels very fast. And due to that, the disadvantage is that the images are blurry. When you travel very fast, the sensor doesn't get enough time to trigger. And that's where it causes sensor blurriness. So there is a loss in quality of data. And you cannot hover this at one location. It has to keep moving. And then the landing options. It is sometimes not safe to get it landed onto your hands. It has to fall down. Then coming to the multi-rotors that we typically use, they have the options. They have the feature of hovering. We can have flexible payloads. We can increase or decrease payloads depending upon our requirements and limitations. And the travel speeds could be controlled. So this actually provides enough time to obtain quality imagery data for a field. The unmanned aerial system that we are currently using is the Agbot V2, manufactured by the Aerial Technology International USA. It's a quadcopter it has 4 arms, and it has the payload capacity of up to 1 kilogram that corresponds to external sensors. And the flight time with these loads can range from 18 to 25 minutes based on the payloads. The total all-up weight when the drone is in air, it's about 8 kg, and it can fly within speed limits of 0 to 62 kilometers an hour. It uses flight control called Pix4 Hawk autopilot cube, which has all the sensors and connected instruments that control the drone or its motion. And then we configure these drones to fly along a path or to follow certain instructions from the ground. We use ground control softwares such as Mission Planner, Q Ground Control, Act Planner. We are using Mission Planner currently, and we can configure these through various platforms that could be laptop, tablet, or smartphones. So let's talk brief about the multispectral imaging sensor that we are using and the thermal infrared imaging sensor. It has wave bands in the visible, that is blue, green, red, and just between red to the just after the red is red edge. That's a very narrow band there. And then we have the near infrared wavelength range. And at 100 meters of altitude above ground, it provides the spatial resolution of 7 centimeter per pixel. And I think that is a very good enough pixel size to figure out how your crop is doing. The direct outputs from this sensor is a digital geotagged number matrix. That is just a digital number, but not something that you can directly use. Thermal infrared imaging sensor, it is called FLIR Duo Pro R from the FLIR systems. And the wavelength range is in the long wave infrared that ranges from 11,000, that ranges from 8,000 to 14,000 nanometers. And the accuracy that could be expected is around 5%. And the ground spatial resolution that it provides at 100 meters altitude is 13 centimeter per pixel. And same, the output is geotagged, that is GPS location tagged images, and each image is a matrix, and that matrix has all like pixels with different temperature values corresponding to the objects that you have imaged. So what are the best imaging practices? To have good quality data, you should conduct, or it is suggested to conduct your data collection between ±2 hours of the local solar noon. Why? Because during this time, there are minimum ambient light changes. And then the wind speed limit should not go beyond 13 kilometers an hour. The sky condition should be either clear or overcast so that you ensure that there is a uniform light during your images. If you have one image at one location, at a location where there is, say, no sunlight, and you have another image from a different location and you have a sunlight, after stitching or in further processing, you might not be able to conclude what you're looking at. And the next important part is radiometric calibration. So we use the calibrated reflectance panels that you see in the right bottom side of the image. These help us to compensate any kind of ambient light changes within the mission, when the drone is imaging. Although there are minimum light changes, but there could be some. So this reflectance panel actually corrects for those light changes. Then there is an onboard sensor called downwelling light sensor, which measures what is the solar irradiance onto the surface, or what is the light coming from the coming at the bottom of the atmosphere. So that actually helps to correct for the light changes when your sensor is looking at different angles, because when in the flight, your drone sensor might have some tilt for taking images, and due to that tilt, there could be some aberrations due to light changes. So that is corrected using the downwelling light sensor data. And of course, GPS data, which is actually important for stitching these images, the snapshots that you collect from drone, and then later geospatial analysis. For example, you need to find out how your crops, or how is your crop physiology or your soil status doing at different location of the field. Moving further, before you fly the flights, you need to ensure some of the things which are critical. Ensure that your propellers, cable connections, and memory cards are in good condition. They have enough storage space and they are safely secured. Batteries. Buttons on the remote control towards the initial locations before takeoff. The drone connected to the ground control software that provides you real-time navigation of how your drone is performing. Check your battery level, drone GPS signals, and flight modes. Check the sensor storage, that you have enough memory card space for the images that you collect. Working DLS, that is downwelling light sensor, signal strength of the GPS signal strength of the sensor. you should collect reflectance panel images before and after the flights. So this is before the flight, and then you should have a planned mission, the decided path of your drone which it should follow to cover the area that you want to image. Next is a configuration of thermal camera that also comes with an app called FLIR US, where you can set the image format, image capture modes. You also need to set some of the approximate weather conditions, whether it is cloudy, scattered, or clear sky, and then approximate emissivity settings. Emissivity corresponds to the object that you are imaging. For the plant, it's quite high, around 0.98. So you can have that setting in this app. And then after that, you are ready to fly. And once you are done with flying, you need to ensure that you have everything you want. The data that you acquired, you have the reflectance panel images, you have your drone turned off, you have your batteries disconnected, and everything secured. Because once you leave the field, you cannot get back the important data that you miss. And the next day, the conditions might not be the same. So ensure that you have everything what you need for further processing or the decision that you want to make from your data. Now, how do we make sense of the imagery that we have just collected? We have tons of imagery, but we want to look at the map or geospatial scale data, that how your crop or how your soil or how your is there in disease, or how is your water use doing at different locations. So you need to have an image stitching and photogrammetry software for this purpose that provides you a stitched orthomosaic. Orthomosaic, I mean with the map, exactly like a Google map, but of the area that you have imaged. So there are some softwares available for it: Pix4D, AgSoft, Open Drone Map, and Drone Deploy. These are currently all paid softwares, and these require different templates when you want to process different kind of data. For example, for thermal imagery, you need a different template. For multispectral, you need a different template. We'll see those details in coming slides. So yeah, initially, let's talk about the multispectral image processing. So you have these snapshots, and you feed them snapshots to the software initially. And then you select the correct template. Since we are having these as multispectral images, we need to select Ag multispectral template in the Pix4D mapper software. And then you can click on start stitching, and it shows your progress, and then it computes the tie points. Tie points correspond to the common points between different images that are used for stitching. More details of the Pix4D will be explained you in the later seminar series by Momtanu Chakravarti, who is working at Pix4D. And then the output is, now this is where we use the radiometric calibration, the images that you took of your panel. You know the calibrated values, and then you get a stitched reflectance map of the area that you wanted to image. On the right top corresponds to the map in the blue band, blue wavelength range. The second, the green wavelength range, red edge, near infrared wavelength range, and so on. Similarly, for the thermal imagery, when we want to select those when we want to stitch those data, we feed those snapshots in the same manner to the software, and we select the right template, that is thermal camera template, and we get this stitched temperature orthomosaic. We don't need a reflectance panel for temperature image calibration. Now, after stitching, how do we proceed? Now, we want to see that how your crop is doing or how your soil is doing at a particular location within the field. So for that purpose, we need some geospatial data analysis platforms. What are currently available? Some of them are ArcGIS, NV, and QGIS. ArcGIS and NV are paid softwares, and QGIS is a free open source software comes with tons of plugins and also inbuilt Python scripting. So if you want to program and perform certain calculations on your or algorithms on your images, you can program using the Python script inbuilt to the QGIS. Some of the stable release versions are 2.18.16, 2.18.22, and 3.10, which are compatible with all the operating systems. I'll list off some examples how you're using QGIS. So first is like orthomosaic import. You just pull the data, the stitched images from the Pix4D software that I explained previously, and pull it on the QGIS panel. And then you have numerous toolbox and plugins. These are developed by open source contributors and to process images in different way for different objectives. So installing plugins is very simple. You just click on plugins and then search whatever plugins you need. And information for these plugins can be found in the QGIS knowledge base. You can simply Google QGIS knowledge base, and you can find different sets of plugins and the objectives that those plugins will be fulfilling for your data. Yes. Moving on, this is one of the example of a commonly used tool called raster calculator in QGIS. For example, calculating green NDVI, green normalized difference vegetation index, which is also regarded as a chlorophyll indicator or the nitrogen status indicator. So you have a near infrared wave band and you have a green infrared wave band, the reflectance in these wave ranges. You simply select the raster calculator as shown in the figure, in the bottom figure, and you get this window. You simply need to select those reflectance maps that you want to use for calculating the G and DVI. We have the formula listed. The reflectance in near infrared wavelength minus the reflectance in green infrared wavelength divided by reflectance in near infrared wavelength plus the reflectance in green wavelength range. And then you get this staged index. And then when you want to estimate or map what is the information at different locations, there's a provision to draw polygons or the areas of interest. And you just use the tool zonal statistics. It will give you all the details, the mean, median, standard deviation, minimum, maximum, and those selected regions of interest. And when you have data from multi-source, for example, we have data from thermal sensor as well as multispectral sensors, both use their own GPS signals, GPS source. So sometimes there could be differences in GPS data acquisition due to different number of satellites that they match up with. So those can induce some of the errors between images. And when we want to, process these images together, we don't want that the calculation should go wrong in one image and right for the other image. So for that purpose, we georeference these images and we use a tool called georeferencer. Now moving on towards our programming. This is a high capacity geospatial data analysis software, and it's just not statistical software, it's much more than that. It has tons of packages and is capable of doing immense machine learning algorithm processing. Another thing is you can also use R for geospatial data analysis instead of QGIS for some of the operations, but one of the requirement here is you need to have accurate GPS locations of your target area or the objective that you're looking at. But in case of QGIS, it's all visual, so you have more user friendliness there. Now, briefly explaining about the metric energy balance model. This is part of my PhD research that we performed study on. So some of the basic equations are estimating net radiation on the surface. That is algebraic sum of the radiation falling onto the surface and radiation reflecting back from the surface. So there is the radiation in short wave wavelength range, and there's the radiation in long wave wavelength range. Then computing the soil heat flux, that is the heat that gets lost to the soil. And then comes the automated extraction of the hot and cold anchor pixels, as I mentioned previously. So there are conditions. If these conditions are fulfilled, these pixels are either cold or hot. And then they are used to calibrate the energy balance and calculate the sensible heat flux later. Then coming down is estimating or calculating the latent heat energy from the net radiation, soil heat flux, and the sensible heat flux, which gets converted to the instantaneous evapotranspiration in millimeters per hour. And then we calculate the reference ET, that is evapotranspiration for the reference crop, that is here alpha for the 24-hour period. And that when multiplied with the instantaneous ET, the reference ET fraction, that gives us the water use for the 24-hour period. We'll look upon some of the code blocks which are used in this R software. So there's a package called water in R that was developed for processing satellite imagery to estimate evapotranspiration. It was developed by Olmedo, and you can find this research paper as cited below. So you can find this package in R GUI, and it's free to install. So every component that you get from this R package is an image. and the inputs that we provide is an image. And ultimately what we get, evapotranspiration, is also a map or orthomosaic of the entire field that you want to image. So we modified this package for the US based sensors and US platform, because this package was originally developed for satellite data. And since we have different sensors from the satellites, thermal sensor, thermal infrared sensor, or the multispectral imaging sensor, and so there were pertinent algorithms that we modified, and we turned into a new package called ETUAS. The inputs that is used by these packages, this package is multispectral data input, multispectral data product that we had from the previous slides, temperature data product, the weather station from the nearest station that helps calculation of reference ET, the digital elevation model, and the flight metadata. The digital elevation model is height or elevation of every land pixel. So if you imagine that there's a bare soil or just a land surface, there's a difference in elevation. These differences in elevation of those areas also sometimes leads to loss of heat, but that majorly occurs in hilly or terrain regions. Next is flight metadata. That is the time of the flight, what was the solar irradiance during that flight, and that kind of information file is also needed as an input. So just a small code block where we start is, we first define the region of interest. For example, we have collected images for a particular area. Within that area, if you want to define another area, then you first input those coordinates. Secondly, you read the weather data file for the nearest weather station. Once that is read, you provide the input for the orthomosaics that you generated in the previous slides as we have seen before. Moving on, what computes is incoming shortwave radiation, the surface albedo, which is actually the ratio of the light reflected from the surface to the light falling on the surface. And that also plays one of the important role towards calculating the energy that is lost. The leaf area index, and these are the pertinent maps or the images or the orthomosaics that get computed from the inputs that we used. The incoming shortwave radiation, surface albedo, leaf area index. Moving next, as a next step is computing outgoing long wave radiation that considers surface temperature as an input and the emissivity. Emissivity is calculated using leaf area index. So if you see the first function there, it uses inputs as the leaf area index and the TS. TS is surface temperature. And then you get that pertinent map as you see in the left bottom. Similarly, it calculates, in the next step, it calculates incoming long wave radiation. That is the radiation that is falling from the atmosphere to the surface. So that is proportional to the air temperature. That is obtained from the weather station. So if you could see that input line, weather station, from that weather station data, we just take out the air temperature data to calculate the incoming long wave radiation. And ultimately, at the end, we sum up these all short wave radiation and long wave radiations falling on the surface and those which are reflected back from the surface, we get the net radiation. And then from the net radiation, there's a direct relationship with the soil heat flux that uses surface albedo, leaf area index, and also internally calculates the NDVI to estimate the soil heat flux. So these are the major components here. And in the next step is estimating the hot and cold pixel, or determining the hot and cold pixel. So if you see in the left bottom image, the hot pixel is represented by the red marker there, which is on the farm road. The farm road is not transpiring because it is assumed to have zero moisture status, so it won't be transpiring. So that's a hot pixel for the model. And the blue marker is on the healthy vegetation, assuming that it's transpiring at its full rate. So these pixels are used to calibrate and then calibrate the energy balance and then calculate the sensible heat flux. And at the last, once we use the basic energy balance equation of the net radiation, soil heat flux, and sensible heat flux, we get latent heat flux as an output. And before that, we calculate the 24-hour reference ET using the Penman-Monteith model, Penman-Monteith equation that many of you might have heard of. And we use the reference alpha crop. And then from that latent heat flux, when we multiply it to the latent heat of vaporization of water, we get the instantaneous ET in millimeters per hour. And then from instantaneous ET, we get the daily ET for the 24-hour period. So these are some of the basic equations, implementations within the package that we modified from a generic package called water. And this study we published recently in the Jones Journal about high resolution geospatial ET mapping of irrigated field crops using multispectral and thermal infrared imagery with metric energy balance model. You can find this paper in this web page. So I'll be now focusing on the research where we used our study, or where we use these algorithms to estimate evapotranspiration or map evapotranspiration for different crops grown in Washington. So we selected 4 prominent crops here: the grape, hay crop, that is alfalfa, the spearmint, and potatoes. So this slide shows different crops with pertinent irrigation systems being used. The potato was using center pivot irrigation system. Spearmint also used center pivot irrigation system, as you might have also seen in previous Dr. Troy Peters' slides. And the alfalfa crop uses wheel line irrigation system. So these are the maps that could show clearly the comparisons between the ET mapped in satellite-based images, that is conventional approach developed for Landsat satellites. And the second one shows you the ET from US images, that is US metric approach. And you can clearly see how we can distinctly identify or distinctly quantify the amount of water used at different locations. And on the top right side, if you see those blue lines or blue shades, these are basically reflecting the soil profiles there. So it tells you a lot more story compared to a Landsat image, and in more accurate manner. That could be helpful towards regulating your irrigation practices. Similarly, the observations were for potato crop and alfalfa crop. So what we are trying to say here is, from the US or high resolution images, you have more potential to assess the variability or actually map what is going on in your field at different locations. So statistically comparing, we had good correlation with the conventional approaches, but yes, US-based approach outperformed the conventional Landsat metric approach for estimating variation in crop water use. That was ranging up to 25% with US imagery, and that was only up to 11% for the Landsat images. The next crop that we selected was wine grape, which is one of the most important crop, and Washington State is the second largest producer of wines. And this image is from the Kiona commercial vineyard, where we got our experimental plot located, and we have good collaboration with the growers around here. So they actually help us in performing research by providing some specific sites for our experiments. So this highlights the common or some of the irrigation practices followed for the grape vines. The first left image shows the surface drip, where the irrigation line is dropping the water from the emitter drop by drop onto the surface near the roots, near the surface, but in fact on the surface. And the second image shows you the emitters that are buried inside the surface, and they are providing water directly to the root zones, either at 40 centimeters of depth or 60 centimeters or 90 centimeters of depth. So the first irrigation line is applying water at the surface using drip, and the second is applying water at the direct root zone using the subsurface drips. So we had our experiment planned in this plot, where we had different irrigation rates, and we had different depths of irrigation, that is at different depths where the water was applied in the root zones. And initially we compared our estimates with the conventional approach, that is Landsat metric. And we can see in the top left side that we have crop water use estimated distinctly for the crop rows. But in the Landsat satellite-based ET map, we cannot see where is mainly important when you have the inter-row regions which are not irrigated at all, and you are just focusing on the crop row which is actually irrigated. And then the left bottom side indicates that there was a high spatial ET variability assessment potential with the US-based imagery. This explains the story more clearly, where we have segmented out all the soil or the background layers, and we have just blown out the crop rows, and we are just focusing on the water used by the crops. So this is one of the major advantage of using the US-based imagery at high resolution. And then this is a comparison of the effects on the water use as a result of different rates of irrigation and the depth of irrigation where it was applied in the root zone. And we could see that the evapotranspiration or the crop water use at 100 or 80% of the commercial rate transpired more than the vines irrigated at 60 or 40% rates. Similar observation was also consistent for 2019 season. And then we also developed some of the temporal crop coefficient using high resolution images. Although the first image looks similar with respect to the standard curves, but 19 season, we can see the crop coefficient that we obtained from images like having different variation than the standard approach. And that's where actually US-based images provide you an actual true picture of your field, but the standard approach, but the standard curve doesn't consider that. So how do we summarize them? So coming from the drone-based images, the output of the evapotranspiration could be mapped in real time or near real time, and that could be used to control your irrigation, the variable rate irrigation. If you see the left bottom image, at some locations it's applying a lot of water, at some location it doesn't. So that's a spatial variable rate irrigation, and that's how we could practice smart. The aim would be here more crop per drop and saving enough amount of water and not losing it. So I would like to acknowledge all our funding agencies, USDA, NIFA, and College of Agricultural, Human and Natural Resource Sciences. We also thank the manager of Kiona Vineyards, Mr. Scott Williams. We thank Mr. Austin Carter for his assistance in data collection. Thank you all, and thank you for this opportunity, and I'm happy to answer any of your questions.
Thank you very much, Mr. Abhilash. I will, by your permission, I would like to ask some questions from chat box.
Please.
Okay.
Yeah.
Thank you. Abhilash, Dr. Siddhi Juikar from Reliance, she is asking for small area around 1 acre. Are these technologies applicable? How we can study for the same?
Okay, so my just a follow-up query will be, you're talking about just drone imaging, or you're talking about its ultimate application towards irrigation management?
This application of irrigation management.
Okay, so initially I would say this is in its initial phase, but if I have to visualize this, if you have a drone image estimated ET, it could be either for 1 acre area, for an example. And if you're practicing controlled irrigation, such as either drip irrigation system, then you can have your field divided into different zones initially when it comes to applicability, and then you can control the irrigation in that different zones based on the water use that you estimate. So yes, I mean, there is potential, but of course we'll need more fine tuning and trade-offs.
Thank you very much. Aishwarya Gawande from MPKV Rahuri, she is asking, what is surface albedo? Okay, great. So surface albedo is the ratio of the light reflected from the surface to the light falling on the surface. So if you imagine that there is 10 watts per meter square of light falling on the surface,
8 watt meter is reflected back to the atmosphere. So 8 by 10, 0.8 is your surface albedo. So that's property of the surface that you are imaging.
Thank you very much. There is one more question. Okay. From Dibakar Ghosh, ICAR IIWM Bhubaneswar.
Yeah.
Is it possible to schedule variable rate irrigation based on crop canopy temperature through infrared thermometer attached with drone?
Infrared thermometers.
Yeah.
Okay. So I would say you don't need to attach infrared thermometers to drone, because the thermometer gives you a point temperature data. It doesn't give you a matrix of data. And then you cannot visualize, or it would be difficult to generate a matrix. And you will have enormous flight time requirement, because you need to sample different points in the field. And if you are expecting that you get a map for the entire field, I mean, it will take decades to complete the mission for a field. So because it just measures you a point, gives you a point temperature data compared to the whole matrix of pixels.
Yes, thank you very much for your answer. One more question from Bala Guru, HCRI Tamil Nadu University. Which is the best timing in a day to operate the UAV in field for getting clear and precise data?
Yeah. So as I've mentioned in one of the slide, you should plan your missions between plus minus 2 hours of the solar noon. For example, in India, if your solar noon is around 12 p.m., you should plan your flights between 10 to 2 p.m. because there are minimum light fluctuations there. And of course, you should use the reflectance panels that are calibrated reflectance panel and have measures of the incoming radiation, because that will help you to correct your data.
Thank you, sir. One question from Cameron. How is adaptations of drones images capturing in multi-cropping or intercropping system?
Okay, so if I understand correctly, how is image captured for multi-cropping systems, right?
Yes,
so
sir. Yes.
One of the query is the multi-cropping practice like side by side, like row by row, or if you have a tree crop and then on the bottom you have some field crops? So I'll answer for both the queries, say. So if you have one row of the tree crops and one row of the field crops on its side, of course, the images will be clearly enough to show the variations for those crops, because drones doesn't know actually, or the camera doesn't know what exactly it is imaging. So, but in the other scenario, if you have crops beneath the tree canopy or the tree row crops, it would not be possible to, it would not be necessarily possible to capture those crops when you are imaging at 90-degree facing downwards. Especially I'm talking this for the multispectral sensors, because they have to look at nadir, that is pointing 90 degrees from the horizontal. It needs to look straight down. So those crops which are grown beneath the canopy of tree crops or the tall crops won't be visible.
Okay.
Very good. Very good.
Thank you, sir. Next question, Mr. Siddharth Sankal from Denknal has a question. What about albedo and different types of albedo from soil, water, and vegetation?
Okay, so if I just put out the so albedo depends upon the surface characteristics, of course. So for the leaves or for the canopy, they have enough moisture content and they are like dark in color. So the absorbance is much high compared to the white surface or very bright surface. So for example, if you have a white surface on the ground, the albedo would tend to 1. So in that case, if I have to relate it to the soil surface, the albedo will be very high for the bare soil. And if the soil is irrigated, if there is moisture, the albedo will be less. And for the vegetation, the albedo will be much more lesser. So typically, if I would say the albedo for the vegetation would be somewhere around 0 to 0.25 or 0.3. For the soil surfaces, it would go up to 0.5. And yeah, for water, I think I'm not sure about water, but yes, it should be more. It should be like very less, or in fact negative. It can, yeah, it should tend towards 0, because the reflectance will also depend upon the purity of water. If it is a glacier, if it is white ice, the albedo may be like very high because it's white. So color is also affecting the surface reflectance.
Okay, thank you, sir. Next question, Mr. Mahadev Fafat from College of Agriculture, Pune has one query. He asked, can we use UAS in identifying pests in our field?
Pest in your field. Okay, so you can certainly find the pesticide, the pest effects. What are the negative impacts caused by the pests? You may not necessarily focus on an insect that is moving around in your field, and that would be like too small at times. But certainly you need to do some groundwork and find out what kind of symptoms are visible as a result when a pest affects your crop, or when your pest eats your crop. If those symptoms are visualized, you can train your algorithms to identify, for example, the green NDVI. If your pest is affecting your crop negatively, the nitrogen content or the chlorophyll content, if it goes down, that could be identified from multispectral images.
Okay, thank you, sir.
Yeah.
Then Mr. Kolambe Sanket has a question. He asked, upcoming NISAR in bracket S and L band satellite data can be used for evaporation estimation?
So could you repeat that question again?
Okay, sir. He has asked, upcoming NISAR in bracket S and L band satellite data can be used for evaporation estimation?
Okay, so I'm not sure what S and L band means, but I would just briefly elaborate it. So we have satellites with multispectral images, and surely at very high resolution as well, up to say 0.8 meters. But those are not having temperature data. So generally, the indices from these satellites are calibrated with the ground reference data. For example, using lysimeters or the eddy covariance. And a calibration empirical relationship is developed to estimate ET. So yes, it could be estimated, but yes, the accuracy might not be good enough, might not be that good, or it might lack applicability at different geolocations. So it needs to be very well calibrated to use it.
Okay, thank you, sir. Next, Mr. Dibakar Ghosh from Bhubaneswar. He has a question: how we can use drone images for variable rate irrigation in different crops?
Okay, so example, I would start like put out examples. So if you have a tree crops, for example, pomegranate, that's like quite heavily grown in Maharashtra region. So if you have a row of pomegranate trees and you have high resolution imagery data, you can just segment out the pomegranate trees and you can estimate ET for just those trees. And if you are having drip irrigation lines applying water to those trees, then of course you can control that rate directly based on the water they require. Well, on coming to the field crops, for example, potato or wheat or rice or paddy, depending upon the irrigation practices. So if, as you might have seen in the previous lecture with Dr. Troy Peters, if there is a chance of using center pivot irrigation system, you have different spans or areas created. If you just find out in that area what is the rate of water required and subsequently to the next different areas, then you can certainly control that variable rate. You can certainly implement the variable rate irrigation.
Okay, thank you, sir. Next, Dr. Premlata from PDKV Akola asked how QGIS software helps the farmer in agriculture domain.
Okay, so if you talk about the farmers in United States, for example, like if like they're like quite very well equipped with the technologies right now for the moment. So QGIS will basically provide you a visual interpretation of how your crop is doing, or what is your crop water requirement, or if there is any disease or stress or water stress in the field that a grower or a farmer could identify. Or if there is a leak in the irrigation system, for example, at that particular location, he can simply go and fix it. In case of say Indian context, where the irrigation systems are not controlled, it can be just a visual interpretation. Of course, if you are imaging like a lot big area that has 3 to 4 different farms belonging to one person or different person, you can have, for the time being, he can see that what is the water requirement for his farm or for one farm, and subsequently the other farms. So that could help him to estimate or actually control the irrigation water that he is applying. Yeah, that's what. So it depends on the context where growers or farmers are, how well they are equipped towards the technology.
Okay, thank you, sir. Next, Mr. Balaguru from Tamil Nadu Agriculture University has a question, which is the best timing in a day to operate the UAV in field for getting clear and precise data?
Deshmukh, this question has already been answered, I think.
Okay, thank you. Then next one, Mr. Fitz from Cameroon has a question. How is adaptations of drone images capturing in a multi-cropping or intercropping systems?
I think I answered this question pretty much, but I will repeat it. So imagine that in the multi-crop domain, if you have one row of a different crop and another row of different crop, if they are using water at different rates, that could be reflected in the images or the ET map that we generate. But imagine that if there is a row of tall crops, and beneath that there's a row for short crops, and if that crop is not visible from top of the say top view, if they're not visible, they won't be necessarily visible in multispectral thermal images, because we capture those images directly pointing towards the ground.
Okay, thank you, sir. Next, Mr. Macmillan has one query. How can the rate of evapotranspiration be estimated by local farmers in absent of the UAS or in country where drone technology is not implemented?
Okay, so I think nowadays the weather stations have come up at many different locations, and there are many at different regions. So at least, if I would say, they can have a gross estimate of the evapotranspiration using just the standard crop coefficient value, and then that gets multiplied to the weather data derived reference evapotranspiration. That would also give the estimate of ET. If he doesn't have anything, this can also certainly work. I would like to just put out an example. Locally, where I belong to India, near my village, there's a weather station being installed by some agency, and people living around in those areas can see the weather data in their smartphones or in their mobile phones. So if they get the reference ET on the smartphone, and then they multiply with the standard crop coefficient corresponding to that particular growth stage, they can certainly estimate ET at that point.
Just a minute. I would like to say a few things here. Regarding the evapotranspiration estimation, maybe it is the potential evapotranspiration ETO, or the crop evapotranspiration based on the crop coefficients developed locally, or crop coefficients developed by FAO. Mahatma Phule Krishi Vidyapith has developed one mobile application which is called as Phule Jal, and its next version is Phule Irrigation Scheduler. Okay, so I would like to appeal to the participants from India that they can refer to that mobile applications for this purpose, and participants outside India can also refer to that, but then they will have to take the FAO values which is inbuilt in that mobile application. So I repeat again, Phule Jal mobile applications for estimating the ETO locally. So what it does, it fetches the values of the weather parameters that influence the potential evapotranspiration from the Indian Meteorological Department FTP protocol or from the Open Weather Service, and then it interpolates those for that location and then it calculates the ETO. So the Fulejal mobile application gives that value. So in absence of automatic weather station or any sophisticated method, you can use that mobile application. And further to this, if you have already grown crop or if you are planning to grow crop, okay, then if you want to calculate the evapotranspiration of that particular crop, okay, and also schedule your irrigation by specified irrigation method based on the evapotranspiration of crop, then you can use the Fule irrigation scheduler mobile app. Okay, so we'll post the details of both the applications in our WhatsApp group. Thank you very much.
Thank you.
Okay. Yeah, I suppose both the apps are available on the Play Store also.
Yes.
Okay. Yes, sir. Yes. Thank you very much, sir. I will take some questions from YouTube live chat box. Okay. One question from Anandan Palaniwal. What is minimum farm size required for drone-based farming?
Okay, well, that's I would say a typical. I mean, it would depend on the applicability, what your purpose of drone is. So if your purpose of the drone is spraying, so it will have a different applicability scale. If your purpose
that he has not mentioned actually.
Yeah. But I will answer. I'll try to answer both the situations if possible.
Yes, sir, please. Thank you.
So if it is drone-based spraying, it will need more control because the farm sizes in India, for example, are not that big. A neighboring farmer would not want the spray from your field coming into his field. So it will need more control of the spray drift and different other parameters. But when it comes to imaging, also there are some constraints that you don't want to image anyone else's land without his permission. So if that is given, it's just images. So it won't harm anyone and it would estimate the information or it would map the information that you're looking at. So I would say it is still it would be applicable in coming time, or yeah, it's still applicable.
Yeah, thank you. Mohsin, I think we will stop here.
Okay, sir.
Yeah, because I think many of the questions have been answered.
Yes.
So I now request Dr. Sachin Nalode, Head Department of Farm, Power and Machinery, to propose thanks to the speaker.
Thank you very much, sir. And we are at this end of this particular session today, and it was great to hear you. And I hope, Abhilash, in this COVID situation, you are in US, and still be great to see you. You are working very good, and in evening hours, I think it is night hours there. In 10:30 almost. Okay. So thank you very much for your very nice presentation and answering most of the queries with lucid manner, and those who most of the students are there, and those are not acquainted with few technologies, and that's why some basic queries were there. But you have cleared those queries also along with the technological queries from various faculties and scientists. So for your information, we have around more than 1,000 participants who are joining with Zoom as well as YouTube, and those are from 23 countries. So thank you very much for your contribution to this training and giving knowledge to all participants all over the world, like from India, African countries, European countries, even Asian countries other than India, and even US. So thank you very much. I will also thank to our principal investigator, Dr. Goran Tiwar, and co-principal investigator, Dr. Shinde, for coordinating, and our team basically who is working day and night to get these questions, organizing with all the team members and expertise. So thank you, team, and last but not the least, all the participants who patiently listen every word from expertise and asking very good queries, I think, and those queries which are not answered here by expert directly, they will be answered through mail or chat box afterwards. So we will be sharing those queries to expert and we'll get those answers. Thank you very much for joining this session. Tomorrow there will be a session similar to this, and I request all participants to join within time. Thank you
Thank you
Nandalal
very much.
for closing.
Okay.
Thank you very much.
Thank you, Dr. Nalode, sir. Before we end the section, we have few announcement. In spite of our repeated appeals and guidelines, some of the participants have not joined by their names, followed by name of the organization to which they belongs. This is important for recording your attendance during the sessions, to recognize the registered participants and also for security purpose. If found tomorrow not joined by their names, followed by organizations, will be removed, and they have, however, the option of joining YouTube. And then, as informed in the beginning, we shall post one assignment on a WhatsApp group at 4 p.m. Indian Standard Time. All participants are requested to submit the assignment on time and as per the guideline issued on WhatsApp group and on time. Please note that responding to this assignment will be considered for issuing the certificates to participants. So tomorrow there are two sessions. First session will start at 9 a.m. Indian Standard Time. And for that session, Dr. Shinduja Sankaran, Associate Professor, Biological Systems Engineering, WSU, will delivering the lecture on use of proximal and remote sensing data in crop phenotyping to support breeding program. And after end of the first session, we will directly start the second session. And for that second session, Dr. Chongyan Zhang, postdoctoral research associate, biological system engineering, will delivering the lecture on image analysis of UAV based data for phenotyping application. So I request to all the participants to join tomorrow morning at 15 minutes before actual start of the session. So I asked to co-convener Dr. Sunil Gorantiwar, sir. Shall we stop, sir? Yeah. Okay. With the permission from the co-convener, organizing secretary of this training program, and today's speaker, we will like to close the session. See you tomorrow at 8:45 a.m. Indian Standard Time. Thank you, one and all.